There is a surprising amount of foods with dairy in them. Being lactose intolerant, I know how difficult it can be to find things that don't make my stomach upset. Cooking and going out to eat can be hard since dairy-free options can be more expensive and hard to find. I find myself trying to remember to take lactase pills before I eat and failing a good amount of the time. But I know I and many others like me are looking for a better and more autonomous way to fix this problem. Today we are going to propose to you a different approach to helping lactose intolerance, this being the duodenal lactase stint. My name is Olivia Petropoulos and I'll be presenting with Henry, Karina, and Billy. So first we have our problem, and this is lactose intolerance. Someone with lactose intolerance does not produce enough lactase enzyme for the amount of lactose consumed, causing adverse side effects. Lactase, as we can see from this photo, is a brush enzyme that requires lactose to move to it. So if we're able to increase the surface area of the lactase to allow a biological reaction to happen to hydrolyze the lactose within the gut, it cannot reach the colon and cause issues.
65% of the adult population around the world suffers from lactose intolerance. Lactose intolerance only increases with age and no significant improvement has been found with over-the-counter medicine. A lactase stent can provide a long-term solution for patients that can be easily maintained.
So some current treatments out on the market right now include lactase pills, addition of lactase enzyme to meals, and last but not least, lactose-free diets. Unfortunately, all these treatments require the individual to always add additives to their food, or none at all, as in no lactose consumption. However, our solution is a method that is a long-term and of a more straightforward option, as it requires no pills with meals or any lactose-free diets.
And this is our approach and what it will look like. It has a nitinol backbone with cellulose nanofibers attached to them, the ends capped with polyurethane to hold it all together, and lactase to then be immobilized in the fibers. It's important to know how this device gets inserted and removed. Insertion is done using a guiding rod and a sheath to compress the stent. It gets implanted in the duodenum, and which is right after the stomach, but in a way that it won't hold open the pyloric valve. In this next slide, we can see the easiest way to get advice inside the body is in tandem with an endoscopic procedure. So the image shows the route of an endoscopic procedure, which is right in line where the device is to be placed. It's also important for the stent to not obstruct the bile duct in this area. This can be avoided though during insertion and through controlling the density of the fibers on the stent in that area. So as I said, for our approach, we start with the nitinol and the cellulose. So the device first requires a backbone to provide radial strength of the stent. Nitinol, which is a mixture of nickel and titanium, was chosen for the backbone for its great shape memory, reducing steps in insertion, its strength, flexibility, and biocompatibility. With the stent made, nanofibers from the cellulose are attached to the stent by means of electrospinning. And electrospinning is a way to produce very thin fibers by means of electric force applied to a polymer melt as it's pushed through a nozzle. So cellulose was chosen for this due to its elasticity, enzyme immobilization, and ease of processing.
Next, our device will have polyurethane caps attached to it. Polyurethane is relatively cheap and easy to use, and also has a relatively low degradation rate in the human body, giving our device a long survivability. It also helps to bind the cellulose fibers to our nitinol backbone. Next, lactase is immobilized on the surface. The CNF fibers allow for a larger surface area, which allows for more surface interactions. And we attach the lactase via covalent bonding to the cellulose scaffolding. Here's a basic outline of our manufacturing process. First, it starts off with electrospinning the fibers onto the stent. Next, it's capped to keep the fibers in place. Next, the lactase is immobilized onto the cellulose fibers. And finally, the device is sterilized and crimped for implantation in the body. Here is a basic outline of a lactase immobilization procedure. All enzymes are attached via a ligand. In this case, we're using cyanogen bromide. Here, the cyanogen bromide will bind to the hydroxyl groups in the cellulose and present that nitrogen atom. Next, an amino radical will be added to rip that hydrogen atom off the nitrogen atom, exposing that nitrogen atom for covalent attachment to our enzyme.
So The design specifications are shown here with the thickness of the backbone, polyurethane, and the nanofiber layers. The inner and the outer diameters are 22 and 24 millimeters respectively, while the backbone consists of nitinol wires that are 0.2 millimeters in diameter. The polyurethane cap is also 1 millimeter in thickness. As for the length of the stent, we've averaged from 60 to 100 centimeters. However, this is variable as different sizes of the stent can be produced to cater different people in order to meet their specific needs. The major key takeaways from this is that the diameter of our stent is very comparable to that of the small intestine, and the stent comes with flare ends at both ends to prevent stent migration upon implantation.
Here's a table showing what testing we will do to our device. The first one is a food chemical products unit determination. This unit is used by the FDA to categorize enzymatic activity in food. And it's necessary for us to obtain this unit if we want to compare to our competition on the market already. Next is the flow cell test. The device will be put into a flow cell with a constant flow rate. Lactose will be passed through and allowed to interact with the lactase. And by measuring the concentration of lactose out, we will have a number for the efficiency of our device under ideal conditions. Next, the stent will be radially stressed to determine how much fatigue it can take. During this time, we will measure the nickel ion leaching as well as lactase efficiency during cycles of stressing. Once these are complete, we will move on to an in vivo model using both a rabbit and then a large animal intermediary, that's pig. This will allow us to determine the effectiveness of our design as well as a real value for nickel leaching in our device.
To elaborate more on the animal trials that will be conducted, our study will consist of a number of rabbits implanted with the stent and fed lactose in increasing concentrations. Rabbits, like humans, are born able to digest milk, and as they get older, their tolerance decreases. They are also commonly used in gastrointestinal studies. Thus, their stool will be monitored to determine the lactose concentration leaving. This can tell us how efficient the device is at varying volumes of lactose. It will also help us determine the closest value for the device, the closest lifespan value for our device in humans, as well as being able to determine the biocompatibility of our device. A pig model will be used as an intermediary model before human testing under a similar procedure.
So some of the major expectations we foresee in the future, as previously mentioned before, are the strong radial strength from the nitinol wires, as well as the shape memory properties of the nitinol material. Additionally, we can expect great elasticity and enzyme immobilization from cellulose fibers. As for the potential obstacles we may encounter, they are listed on the right. These include nickel toxicity, stent migration, cellulose fibers falling off, and so on. Some of these problems were addressed previously with design specifications and testing, such as stent migration, nickel toxicity, and blockage of the bile duct.
In this slide, we outline the costs that we estimate for the production of our device. We estimate the greatest cost to come from the endoscopic procedure. The average cost of this procedure should be slightly under $3,000. For the benefits, a person with lactose intolerance can spend up to $1,400 a year if using a Lactaid every meal 3 times a day. Our procedure is estimated to cost around $3,000 without insurance and should last up to 2 years. The cost of our device is similar to what one would spend on Lactaids and eliminate people's need to purchase Lactaid products. It also comes with the convenience of being able to eat anything without having to worry to take a pill or a Lactaid supplement.
So the main target audience for our stent will be adults. And among these adults, we aim to help people that struggle with lactose intolerance, whether it be severe or mild symptoms. Since our method is also a hassle-free solution, people who struggle with memory loss or cannot remember to take pills can also benefit from our stent.